Welcome back, my dear students. In the video, this is the last section. We are to discuss this in the chord properties of a circle. Right, we have got two more theorems to discuss here, and they're all about the intersecting chords. Right, so it's just like when chords intersect each other, we are specifically looking at the chords which can intersect inside the circle like this. Right, what is it that we expect, and what knowledge should we get from this? And somewhere we also have the chords which can intersect outside the circle, right? Like this one here, this is the chord, and this is another chord, like that one. They can be extended out, like this, and you find that somewhere they're going to intersect outside. Here is the point T, and here is the point T. What is it that we should know about this chord and that chord when they intersect inside the circle? And what is it that we need to know, the type of property we need to know when this chord intersect with that chord outside at point T. Right, so to begin with, we are going to discuss something about chords which intersect inside the circle. Right, so chords intersecting each other inside the circle, what property should we know about it? Right, so let us be together here and discuss about the intersecting chords which intersect inside the circle, and let's see what is it that we're going to expect out of it. So we have here chords intersecting inside the circle. Can you try to draw the diagram? In your case, I'll ask you to do that. I think we should be together. Sometimes you should be able to have a paper each time you are watching these videos, so that when we discuss, you try at least to scribble somewhere and even do the practice as such. Right, so like here, I'll have my chord. One of it, I'll draw it like this. Another chord, I'll draw like that. These chords can be defined as AM. One chord is AM, the other one, let's have this as TB. The two chords AM and TB are intersecting at point F. Let the two chords intersect at F. Right. Now, if we can try to join point A to T and point B to M, we'll find something that is very interesting. That is always true about a circle each time the chords are found to intersect inside the circle. Right. So we would like now to trip that one out. What is it that we need to know about the chords which intersect inside the circle? Right. So here I will not first of all review it, but that will come out after we've done a certain kind of a proof, the result of which should be considered as true, because that will be true for all the circles that you can draw, and those circles have got the chords which intersect each side. So that's why I asked you to draw a circle like this one here. Draw two chords intersecting like this at one point, say F. Now let's follow this one. Our interest is about chord T, B, and A, M intersecting at F. So about it, can you try to connect A to T like this to form a triangle AFT, and connect B to M by joining through the line which is BM? Right. Once we have done that, you'll be able to appreciate that we have got two triangles there. You talk of triangle AFT and the triangle BFM. The two triangles have been generated from the two chords after joining A to T and B to M. But remember, our target are the issues related to AM and TB. There's the ones which are intersecting inside the chord. But now here, we'd like to retrieve that information by using the two triangles here. Right. If you can look at the design of the two triangles here, you'd be able to appreciate that somehow, those triangles are similar. Right. So I'd like us to show that the two triangles AFT and BFM firstly are similar. So this is the results of which will give us an idea about what it is about the two chords which are intersecting inside the circle. So if you'd like to show that two triangles are similar, there are so many conditions that satisfy the two triangles are similar. One of it is the equiangular test, that the three corresponding angles in the two triangles are equal, then the two triangles are similar. Then let us use that condition to show that triangle AFT and triangle BFM are similar. Right, so here we need to show the AAA test, angle, simply say equiangular. Right, let's begin up with the first A, letter A, meaning that a pair of corresponding angles are equal in the two triangles. So you'll be able to see that firstly, if you can talk of this angle here, I'll define it as angle A. You define that that angle is the same as angle B here. Right, angle A is equal to angle B. The reason of which is highlighted from the first property we discussed about angle properties of the circle. You're going to appreciate that this angle A at A is subtended by arc TM, and this angle B at B is subtended by the same arc TM. So it's just like angle A and angle B are subtended by the same arc. So these two angles are equal. And you can write that one as the first test. You write angle A is equal to angle B. Reason, angles subtended by same arc. Right. So we have done with the first A. We'll be able to show the two angles which are equal. Let's go for the second letter. We need to drive out the other pair. So here you can also see that this angle here that we have here at F, which is angle AFT, and in this other triangle I've got angle BFM. These two angles are equal. You can refer to the properties we discussed in Form 2. That's the when lines are crossing each other, straight lines, we have got a pair of opposite angles. So here you'll be able to see that this angle and that angle are vertically opposite to each other. So the angles are equal. So I also like that one, satisfying the second letter in the similarity test. So here we have to write, let's say, angle AFT is equal to angle, that is what? B, we talk of BFM. BFM, like that. Why? Vertically opposite angles. Right. Next, we have the last A here in the equiangular test. That also signifies another pair of equal angles. So in the two triangles. And moreover, I think the last letter should not even bother to work out on it. We can just conclude that as much as two pairs of corresponding angles are equal, we expect the third pair again to be equal, because we all know that the sum of the interior angles of a triangle is 180 degrees. So if the two angles are equal, what do you expect of the other, the third angle? They must be equal. But anyway, still more as designed here, we still more have to work out separately, or that using the issues about the third angle, still more we'll be able to see that that angle that is remaining, in this case angle T and angle M in the other triangle here, these angles are equal. You'll be able to see that the two angles T and M at T and M are both subtended by the arc AB. Arc AB is subtending an angle at T, arc AB is subtending angle at M. So expect angle T being equal to angle what? Angle M. So here we are, we need to write that down. So we have our angle T is equal to angle, that is what? M, as such. Reason, angles subtended by same arc, like that. So we have managed to at least be able to show that the three pairs of opposite, the three pairs of corresponding angles in the two triangles are equal. So the angular test has been what? Satisfied. Then what do we say? Then therefore, triangle, now you go by the letters of the corresponding angles in that case. So here you go like, if I'm to describe the first triangle, as AFT, AFT, I also have to follow the same order of letters that say which angle is equal to A. So if I'm to describe the other triangle, I'll go by, in this case, like A in the first triangle is equal to angle B in the other triangle. It means when I'm describing the other triangle in the similarity, I have to follow that order. So I've started with angle A, then I got for F, then T. It means here I'll also go the same. If I started with A, for this triangle, I'll begin with B. Then I'll go for F and I'll finish with M. Right, so I'll write here triangle AFT is similar. Similar to triangle, now it will be BFM. BFM. Reason, angle, angle, angle. Right. So about what we discussed about the similarity is that if triangles are similar, what do we expect about the ratios of their corresponding sides? We really saw that is the same from two work that say if triangles are similar, it means the length of corresponding sides, talk of the ratios of the corresponding sides must always be equal. What does that mean? It means what we have here, we expect that say by the letter that we have here, if we take any two letters, the defining sides, it means that say if I take AF, a ratio of AF to ratio of BF, that must be the same as the FT to FM. And that should also be equal to AT to BM. That's the way it is. You can even try to measure that to be able to find that the ratios of those corresponding sides are equal. So what are we going to write here? We write the same. AF to BM, F, in that order. But how we write? We prefer to write in this form, that say AF, instead of writing 2, like BF as the ratio, we write it in a different form like a fraction to say AF2, that is BF. This is the ratio to say AF2, BF. This must be the same as FT to FM. And then AT to BM. You follow the order of the letters because the triangle has already been proved to be similar. Then the order of letters also defines the equal talk of maybe angles and of the sides which are also corresponding to each other. But if you write the in the different order of the letters, that may not signify which parts are corresponding to each other. But when we are concluding the similarity issues about the triangles, we always have to write the letters in order of their corresponding parts. Could it be sides or the angles? Like, so this is our expectation. All triangles which are proved to be similar, we should expect that the ratios of the corresponding sides must be equal. So our target is this part here. This is where we're going to retrieve what we need to know about the intersecting chords which are inside the circle. Remember, our discussion is simply about chord AM and TB. That's our discussion here. What is it that we should know? So I've just taken you far to know what we need to know by proof. Like, so that tomorrow you just say, how come that this is about this? So we say by the similarity, this is true about the intersecting chords inside the circle. So now, what do you have here? Here, I'll just choose the ratios which are defining the issues about the parts of the chords which are intersecting inside here. Our chords are TB and AM, which are intersecting. As far as the intersecting, you see that the chords are split into 4 parts, which is defined as the AF, FM, BF, and TF. So here we just like a matter of looking at the, or say realizing the relationship that is there amongst the 4 parts of the intersecting chords, which are 2 here. How do they relate to each other? Right, so that relationship will come based on the what? This knowledge here about the ratios of the corresponding sides. So here I'm going to choose the ratios which are defining the parts of the chords. The first one talks about AF, and BF. So here we have got AF and BF. So I'll consider this ratio here. And the other one talking about FT and FM. FT and FM. So I'll also consider this one here. But AT and BM, AT and BM, they're not part of the what? Chord. They were just lines which were just constructed in order to give us a complete what? A triangle on both sides. Like, so we don't regard them as part and parcel of our discussion. They were just like there helping us to come up with what we need to know. So let us concentrate on the two ratios, AF to BF and the FT to FM. So by design, the moment we say this ratio is equal to this ratio is equal to that ratio, we should expect that any two ratios must be equal to each other. This is equal to that, is equal to that. Then what? Therefore, AF to BF should be equal to FT to F what? M. That's the thing. So let's now try to cross multiply the ratios. So here I'll write by cross multiplication. It means this will multiply by that side. This side multiplied by that side. So what do we have? We have FM, right, multiplied by AF, which would be like AF. This is a symbol of multiplication. When I write a dot here, it means multiplication. Right. AF multiplied by FM is equal to FT multiplied by BF. Right. Or you can write in another way around, meaning the same thing. Some people might feel like the dot means the decimal. No, it simply means the same thing. You can talk of AF, right? This is multiply, but some people can be confused with the letter, the symbol of multiplication to take it like X. That's why I use a different notation as dot. This means multiplication, the product. Right, so here could be this one, AF multiplied by FM, which is equal to FT multiplied by what? BF. So our expectation is this. Right, every time the chords intersect inside the circle, what we expect is this relationship. The chords are going to split each other into 4 parts, and the 4 parts of which are going to be related like this. So here, if you can see, we'll be able to see that if I've got chord A, M intersecting with T, B at F, it means what I have here, I should expect AF, which is the distance from here up to that, multiplied by FM from here up to that, is the same as what? FT, which is FT multiplied by what? BF, which is BF. Right. So if chords are intersecting inside the circle, our expectation is this one, always true. Right. So that one is also, they are used to find the length of the chord and also some distances, maybe of a triangle, if they're drawn. Each time we don't have a distance, exact distance from the center of the circle as such. Right. So just to extend the discussion here for you to understand more and match it up based on the proof, what we have, just like any circle you can draw like this one here. The fact that the circles are going to intersect somewhere like this. Let's have this one as Q, Z. This is D, A intersecting at H. By this, it means QH multiplied by HZ. You see that? Should be able to DH multiplied by what? HA. Right. That's what we have it here. So you conclude by this one as to say QH multiplied by what? HZ is equal to AH multiplied by what? HD. It means the parts, this multiplying by this multiplying by that. The same we also have this side is multiplied by this side, and then that side is multiplied by that side. Right, so this is what we needed to know, that if chords are intersecting inside the circle, the relationship is there existing amongst the parts of the chords which are formed as a result of the intersection. Right. So in the next video, we are there going to look at only 2 examples, and then I'll give you an exercise that you can try, like that are able, that are questions that needs the application of the knowledge that we have had here. Right. So thank you very much again for being together. We have just introduced one property about the intersecting chords. Right. Thank you very much for that.